So we'll get started.
So in the syllabus, we indicated 4 weeks for this first topic coverage. We ended up spending 5 weeks. We lost one lecture due to the snowstorm. So I guess we technically were one lecture behind. So we're going to start with a new module of the course on constitutive modeling. So this course is a nonlinear finite element methods course. We could go in many different directions at this point, given the introduction. As you can see, it's more solid mechanics oriented. The third module toward the end of the course will be something called, which will cover the theory of porous media from the perspective of finite element analysis, or some people call this poromechanics. We'll get to that later. So here we're going to talk about constitutive modeling. So we're going to start with the one-dimensional case. The notes are somewhat detailed, so I encourage you to read the notes, work through some of the equations yourself. Some of this, if you have not been exposed to elastic plasticity before, some of these concepts will be very new. And so I encourage you to refer to the notes. There are also a number of references listed in the syllabus, and these should all be on reserve in the library by now. The first set of references listed in the syllabus are what we call mixture theory or poromechanics, how we treat those together actually, and of course linear and nonlinear finite element analysis or finite element method. For the plasticity coverage, theory and numerical, there are a number of textbooks, and there are more beyond this list. Some of the classical ones are, for example, Lubliner. Actually, I didn't even list. There are more classical references than that. For example, there's what's called the Hill book, which is arguably the first text on plasticity theory. I didn't even list that here, but that's a good one if you want to really go back more to the original idea behind plasticity. But I listed some of the accessible books. So this course, although we're going to cover plasticity, we're going to cover it just enough to get to the point where we have equations that we can then implement with the finite element method. Okay? We're not going to go beyond that. So we're going to touch more on the numerical side of things, which to some extent are covered in this first one by Dunn and Petronich. This is more of a kind of an overview of computational plasticity. More details, of course, are in the Simo Hughes book. This article right here, I listed just for completeness. This is somewhat a little more advanced, the Simo numerical analysis simulated plasticity chapter, because that's mostly gets into a lot of theory and finite strain, but I listed it anyway. Another nice text for computational plasticity is this De Sosa, Neto, Parrish, and Owen book. So anyway, so we're going to get started. Just to give you an idea where we're going. So we're going to start with one-dimensional. So by one-dimensional, sticking to what we covered up to this point with respect to even the elastostatics, nonlinear elastostatics of the axially loaded bar. We're assuming by 1D, in this case, we're assuming uniaxial stress. Okay, uniaxial strain is a different loading condition. So uniaxial stress is you take a piece of material, you put it in a load platen, you either grab it and pull it in tension, or you put it between two platens and you compress it. Uniaxial strain would be you take a material, confine it. This is a classic test in geomaterials or soils. You confine it by some rigid ring or device, and then you compress it, and the idea is that the lateral strain is nearly zero. Okay, so those are two different one-dimensional cases. We're going to look at the uniaxial stress case. It's difficult to talk about even the uniaxial stress case without touching on some of the three-dimensional concepts. So you're going to see some back and forth between tensor notation and the uniaxial stress. Anyway, I'm going to touch on a lot of different things. We're going to get to the numerical time integration, something called the radial return mapping algorithm, the consistent tangent. We're going to need that as well for our Newton-Raphson. And then kind of late, toward the end of this module, we're going to talk about some pressure-sensitive plasticity models, which are appropriate for what we call geomaterials, for example, soils, rock, concrete to some extent. So we're going to start with some classical models, more Coulomb, Drucker-Fogger, a cap, and there are variants on that. Okay, and then hopefully we can get that accomplished within this time frame, such that basically the month of the course we'll be doing poral mechanics, assuming that all works well. Okay? So I know we can't satisfy everyone's interests. Some may want to be seeing this topic coverage now, but you know, this is how I'm going to proceed with the course. Any questions at this point? Okay. Right. So switching over to the notes, like I said, unlike the linear course, we have, for whatever reason, I have my notes in sort of chapter format updated, but my slides are updated. So anyway, it doesn't really matter the order, but so this is what I call one-dimensional constitutive modeling. A lot of the notation is taken from Simone Hughes and then from another more recent textbook by Borja. So we're going to touch upon the main concepts behind constitutive modeling, or the main, what I call steps. But in this course, we're going to mainly focus on, and in this chapter, what we call steps 1 through 5. But I at least want you to be aware of all the steps. All right? Because if you're conducting a nonlinear finite element analysis, you're going to probably touch upon all these things. Even if you're using a code, you should be at least aware of these things. Okay, so let's get started, and then I'll work on the board as well. So kinematics, and I'll have a little drawing on the second page. So basically, kinematics, in some sense, means deformation or motion. So we're not going to, this course is not, I mean, as you can tell, this is a more solid mechanics type of class. So kinematics is a general term, so that could mean rigid body dynamics, you know, throwing the pen through the room. That's not what we're worried about. There are numerical methods that focus on that type of problem, more covered in, for example, the aerospace engineering department. But kinematics in this case is just looking at our axial strain. So let's do that over here. So let me get started. We'll do our board sequence. So constitutive modeling. In 1D. I'm going to clarify this. This is uniaxial stress. Okay, so we're going to have our axially loaded bar problem again, like this. And just draw the picture. You're working on this type of problem for the problem set due Thursday from the perspective of just having a nonlinear elasticity model representing the behavior of the bar. So we assume that the bar is whoops, sorry. Come back. Okay. So we have our one-dimensional approximation down the middle. And I'm going to point out a couple things. So let's say this is x. Okay, so then we would have right-hand rule. X, Y, Z. This is Y. Okay, but x is the coordinate of interest. So the basically then the axial stress is just sigma, which if you think about it, is equal to sigma xx, which, or in tensor notation, we say this is sigma 1, 1. Okay, because we can call these little x, y, and z's, we can call this x1, we can call this y, we can call that x2, and we can call this x3. So these parentheses, x1, x2, and x3, these are not functions of, these are just other names for, okay, x, y, and z. Why is that important? Because you're going to see when we get to the thermodynamics a little bit later, I'll talk about this strain in a moment, that's what I'm trying to get to, is this, that we can write the stress tensor or matrix, so the stress tensor, we can write sigma. And for the axial stress, basically it has only one component, 1, 1. Which in this case is a second order tensor. So you think about it that we only have one component, which we call this sigma. It's the axial stress, and it's right there. All right, so why am I showing this? Because with regard to kinematics, we have something called an axial strain. Okay, so then we have over here the axial strain, which we've already talked about. So the axial strain, up to this point, we've just said it's the derivative of the displacement with respect to, in this case, the axial coordinate x. Okay, we're going to decompose this in a moment with respect to our constitutive modeling, elastoplasticity, axial strain, axial stress. Now, when I stretch this pen or this bar, I compress a piece of material, the stress, or at least we're assuming, and of course the assumptions for those of you who do more experimental work, you're already aware of this, is that this assumption is an idealization. It's assuming that when you do, let's say, a compression test on like concrete or soil or rock or even metal, for that matter, you're assuming that the boundary conditions are negligible, that they're nearly frictionless. We know that's never true, but anyway, that's the assumption we make. Okay. So what I mean to say by axial, so the strain tensor, and I realize some of this is background for, or you've already seen some of this, but for those of you who haven't, I'm covering it. So the strain tensor is again a 3 by 3 matrix or second order tensor, and it has a value epsilon 1, 1, 0, 0, epsilon 2, 2, 0, 0, 0, epsilon 3, 3. And for this case of just axial stretching of this bar, uniaxial stress, epsilon 2, 2 will equal epsilon 3, 3. So 2, 2, 3, 3, so that's the, the YY and the ZZ components. So what we're trying to say here is that you stretch this rod, let's say, or you compress it, either way. So if you stretch it, the Poisson effect will tell us that the bar will shrink laterally. So the ZZ and the Y will have a ZZ and YY component of strain. They'll be equally to each other. And from elasticity theory, we can solve for that. And with an elastoplasticity model in turn, we can additionally solve for that. But what you're going to see in our constitutive model is that we're just going to say that epsilon, this epsilon right here, is just equal to epsilon 1, 1. And it turns out that when we look at the thermodynamics, we're going to see that because the stress only has a component in the upper left corner associated with the x coordinate, when you do what's called an inner product of these two tensors related to what we call the internal energy, the only term that's going to survive is the sigma 1, 1 times the epsilon 1, 1. We'll get to that later. Okay? But the physical problem has the lateral components of strain. Does that make sense? So anyway, we're going to do a three-dimensional implementation a little bit later of elastoplasticity, and we're going to show how the 3D implementation should simplify down to the one-dimensional one. Okay? All right. Okay. So with that said, what we're going to do, these are, this is, as you're doing right now, this We're going to get the displacement field from the finite element analysis. So we're going to know what the total strain is. And then we want a constitutive equation eventually for the stress with regard to the strain. We did the simple nonlinear elasticity model up to this point. But now let's look at the kinematics. So going on here is kinematics. Let's see those guys. Yeah, this guy's already losing its ink. All right, so what we do is we not to get into details, but we say that constitutively, all right, we say that the axial strain this one. Should have brought the other pen. So axial strain. It's almost dead. Yep. Okay. This will be interesting. I wonder if these are probably not very good. All right. Anyway, so the axial strain we're going to assume is epsilon is equal to something called epsilon E plus epsilon P. Okay. Now, notation, as I've said before, is always a problem. This E this E denotes elastic, not element. I know that's confusing. Okay. So epsilon E is the elastic strain. Okay. And then epsilon P is the plastic strain. Okay. So this is, of course, small strain theory. So when you get to finite strain, constitutive modeling, eventually all the different forms of finite strain constitutive models out there, when the higher order terms associated with the what we call nonlinear geometric effects, when they're negligible, they all boil down to something like this. Okay? All right. So what's interesting here is that this will come from FEA. This epsilon P is going to come from a flow rule. So then what we do actually is to calculate the elastic strain, we take the difference. So then we calculate elastic strain. So it's epsilon E equals epsilon minus epsilon P. So yeah, that may seem a little strange, but that's how it works. What's interesting about this, too, is that we'll get to the stress a little bit later, but eventually you can kind of see where this is going, is our Hooke's law is going to be, the sigma is going to be not epsilon, the sigma is going to be epsilon E, the Young's modulus E times epsilon E. Okay? And then you're going to see how the elastoplasticity works. Right? Okay, so let's look at a picture of this, and we haven't talked about stress yet, but this is on the next page, is if we do a stress-strain curve, and we'll get to the experimental motivation as well in a moment, but you can imagine that if we have an elastic loading portion of the curve with a Young's modulus E, and then eventually we get to something, we haven't defined this yet, but we get to something called a yield stress, like this. And then let's say we're loading like this, and then let's say for right now it's something called perfect plasticity. We'll talk more about that later, but what that means is that once you yield the material, there's no change of stress, and then you get to a point, let's say right here. And in the notes, we call that point A. Okay? So let's say that, so we've loaded up to here. So at point A, okay, this is epsilon, let's see, epsilon sub A. So that's the total strain at A. Okay? So we've assumed that this is plastic yielding right here. So this is plastic yielding. All right? So what's going on here? So what happens is that, and we'll get to this more later, what happens is that to get from this point, this initial yield point, let's call this at 0, getting from that point to point A, what's occurring is something called plastic deformation. Okay? However, at point A, we still have stress. The stress is the yield stress. Okay? We're just moving right along here. We just say that for right now, this is something called perfect plasticity. We'll get to more of that definition later. So anyway, so at this point here, epsilon A, we have something called an elastic strain and a plastic strain based on our kinematics. Okay? And what that is the way you can see that, given this simple linear elastoplasticity model, is that if you were to unload elastically here, this is our Young's modulus, then you would come back to a 0 point right there on the stress-strain curve, and you would have what's called a residual or permanent or irrecoverable strain. So the plastic strain is sometimes called permanent irrecoverable. Okay, and then the elastic is the recoverable strain. So for those of you who may do a lot of constitutive modeling, you know that there can sometimes be kind of gray areas between this. But anyway, for right now, for simple teaching purposes, this is what we're going to do. So what this is that this total strain value, epsilon A, right here, is composed of this residual component of the strain, which is the plastic strain, so epsilon PA, plus this little value here, which is the elastic strain. Okay? So at point A, we have a stress. We'll talk about stress later, but at point A, we have a total strain epsilon A, which is equal to an elastic component and a plastic component. And one way to see what these components of strain are experimentally, potentially, is you unload back to 0. If you go through this stress-strain response, let's say experimentally, you get back to here, and you can say, well, my residual strain or irrecoverable strain is epsilon PA, and so this little portion right here is my elastic strain. Okay? So very simple concepts, but that's the idea. Okay. Right. Okay. So something else you see here is that the stress, we'll get to the stress in a moment, but the stress is always calculated, at least from our perspective of this constitutive framework, from elastoplasticity perspective, the stress is always calculated from the elastic strain. Okay? That may seem obvious, but this is a little detail that I hope you take away from this course, because when you extend these types of models for, let's say, to include temperature effects or some other form of constitutive modeling, you should always realize the stress is always calculated from the elastic strain. Okay. So what I mean to say that, so the stress, I'll just make this comment here. So stress calculated from elastic strain. And we're going to just use Hooke's law for right now. So Hooke's law. So we're going to have sigma, for example, sigma at A, so that's sigma y. So let's say sigma at A is equal to E, the Young's modulus, epsilon E at A. Okay? So when we moved from this point 0 to this point A, the stress was staying constant, which means that the elastic strain was constant. What was changing was our plastic strain. Okay? So you can imagine you're pulling your material, the stress is being constant, so the only thing changing is the plastic deformation. You unload, and then you see what that plastic deformation is. Of course, we're interested in how to model that, and that's what we're going to be talking about. Okay, so that's a long-winded discussion of kinematics. Any questions? Okay.
Right, so this is what I just talked about. All right.
So now we're going to get into some subtleties. We're going to get more into the details in a moment with respect to number 2. And this is a really important part of this type of work. So, right, okay. So number 2. So number 1 is kinematics. So these are the steps in constitutive modeling that we should follow. Number 2 is what we call balance equations in thermodynamics. Of course, lumped in thermodynamics is one of the balance equations, which is the first law of thermodynamics, the balance of energy. But of also, more importantly, in thermodynamics is the second law of thermodynamics. We do not want to violate the second law of thermodynamics, so we're going to see how that plays out. But to be complete, one of our balance equations is the balance of mass. We'll get to that more later with poromechanics. But in essence, what this is going to tell us for small strain theory is that the mass density will remain constant. Okay? For finite strain theory, you could imagine deforming a material such that the density of the material might actually change. More importantly for us is what you guys are solving right now with your problem set due Thursday, is you're solving the balance of linear momentum. We solved that for the displacement field using the finite element method. The third balance equation is the balance of angular momentum. And for our purposes, this will lead to what's called a symmetric stress for what we call nonpolar media. Not to get into this, but there are theories, generalized continuum theories, which if it's a micropolar theory, you'll have a balance of angular momentum. There are other theories which I'm interested in working on, micromorphic theories, which have additional balance equations or terms in the balance equation. But we're going to skip that. That will just tell us the stress is symmetric. So what that says, this seems rather trivial, but it says that this tensor will always be symmetric. Now, for our axial stress problem right here, axial loading problem, this is obviously symmetric. But just to make that clear, number 4 is the balance of energy. We'll talk about that. If you had a coupled a thermoelastic or thermoelastoplastic problem, you would use the balance of energy from a coupled finite element analysis perspective as a way to solve for temperature at the nodes. So you guys remember in the linear finite element course, basically solved the balance of energy separate from any of the other balance equations in the form of what's called the heat equation to look at our heat conduction problem. Okay? But you can imagine coupling all these balance equations to do what's called a multiphysics analysis. But what's going to become important for this discussion is number 5, second law of thermodynamics. We'll see how that works out. That's going to constrain our plasticity formulation such that we do not violate the second law, which is obviously important. So this means that we should not get any sort of negative, we should not have we should not, in our minds, imagine a new material that somehow gives us energy. All right? That would be great, right? We'd solve all our energy problems if we had a material that we could deform and we put work into it and it gives us more work out. That would be fantastic, right? We wouldn't have to worry about renewable energy or anything like that. So clearly, we don't want to violate second law. So we're going to focus on 4 and 5. If you're interested in more details, I'm just going to touch upon some of these things. The notes, basically, in my view, just touch on some of the key points. But if you're really more interested in this sort of stuff, refer to a continuum mechanics text of your choosing. I'm just listing a classical reference by Malvern. And then, of course, if you want to go further back, there's the classical text by like Truesdell and Tupin, et cetera. But then there's also Holtz-Apfel has a nice, well, I call it more recent, relatively recent text.
2000.
Okay. Right. All right, we'll get to that more detail in a moment. So, okay. So we covered number 1 is kinematics. Number 2 is balance equations in thermodynamics. Number 3, you may be asking constitutive equations. You may be thinking, well, that's what we've been doing up to this point. Turns out, not really. Not yet. Okay? Constitutive equations, this is really where the art of constitutive modeling comes in. This is where your experience as an experimental mechanics person, or you're just more on the modeling side and you're obtaining data with a collaborator. You guys are working together to derive a new set of constitutive equations. This set of constitutive equations, this is really where you try to match or understand how your model can be calibrated against an experimental data set. And so this is, like I said, where some of the art comes in. For what I want to drive home, I mean, ultimately what we're interested in this course is how do we implement these equations in the context of the nonlinear finite element method. But I also want to drive home how you need to be careful about how you work with your constitutive equations. Okay, so needless to say, and I'm not writing some of these things on the board right now because we're going to get into more detail later, but the simplest constitutive equation we've been treating up to this point is our elasticity constitutive equation. So we use this kind of exponential nonlinear elasticity model as a way to get your feet wet with regard to nonlinear finite element analysis from the perspective of a problem set due Thursday. Because as you're about to see in this topic coverage for elastoplasticity, if we had to wait to cover elastoplasticity, you wouldn't be able to do nonlinear finite element analysis, like write the code, edit the code, do the arc length method, all these sorts of things, because we would have to wait too long. Because this is, and so what we're going to do, what I mean to say by this is we're going to abandon our nonlinear elasticity exponential form model. We're going to go back to Hooke's law, sigma equals E times epsilon, now epsilon E, based on our kinematics over there. And just as a note, this may seem obvious, but if the plastic strain is 0, we just recover what we've been doing, or we did in the linear course, right? So if the plastic, if we don't get to point 0, if we don't get to the yield stress, if we're always living somewhere here on the curve, okay, we're just deforming our material just a very little amount, and we never get to the yielding, then having just elasticity theory is sufficient.
Okay.
And that's what a lot of typical solid mechanics, structural analysis, things like that work with. And where the problems come in play are when you start to have yielding, and then that's when you need plasticity theory. We're going to introduce something in the context of constitutive equations called a yield function. What this does, what makes plasticity theory complicated is that this is basically a constraint. So it's going to make this curve happen, okay? So what the finite element method is going to want to do, we're going to, let's say, we stretch our bar with a prescribed force. Let's forget about arc length for now. Let's assume we can happily go up this curve. The finite element method, if we keep incrementing axial force, which will increase the axial stress, we're just going to keep going up this curve. Now, if we did not have what's called a yield function to constrain our stress, then the curve would just keep going like this. Okay, just elasticity. We're all happy. But what the yield function does is it constrains the problem and says, hey, wait a minute, you can't go beyond this stress. You have to now do something different. You have to go this way. And that's what the yield function is going to do for us, in addition to some other things, the flow rule. There's something called a plastic potential function. This gets a little more conceptual, but for those of us who work in constitutive modeling of materials know this is going to give us some more information about how the material deforms versus how the material yields. Now, you may think, oh, those are similar things, but for certain materials, in particular geomaterials, the way the materials deform is somewhat different than how they actually yield. That may sound a little strange. So from a nuts and bolts perspective, what that means is that in a soil, like a sand, for instance, a dense sand, you do a triaxial compression test on a dense sand, a cylinder of sand. What that says is that the friction angle is basically different than what we call the dilatational or dilation angle. Okay, so that, in a nutshell, that's what that is. And this way of formulating the constitutive equations will give us that flexibility. There is something in constitutive modeling called, some people say, internal state variable theory. Basically, internal state variables come under this framework. What this is we're going to add these quote-unquote internal variables, which are basically phenomenological variables, which try to account for some of the underlying physics that we might be observing in our experiments. Okay. This is where a lot, for those of you who've heard about this terminology, this is where a lot of what's called multi-scale modeling comes into play. People try to better inform these ISVs through some what we call lower length scale model of the grains moving around or the dislocations. This is a whole nother discussion, but we're not going to go there. But I'm just saying that this gives us some flexibility within our model. So we're going to have a Q. And again, notation's always a problem. This Q zeta, I'm trying to stick with some of the notation, for example, in the Hughes book, in the Soso Neto book, and the Borja book as well. So Q typically is reserved for this internal state, stress-like internal state variable vector. But in our heat equation, or our balance of energy equation, we also have Q as our heat flux. I know that's confusing. I try to distinguish between the two by saying our internal state variable vector is Q zeta, and our heat flux is just Q. I'll just say at the outset that's confusing, but that's what we're going to do. Let's see. I know I'm talking a lot, but I'm trying to touch on some different things. In problem set 1, a number of you indicated.
Sorry, that was crazy there. All right.
Some of you indicated interest in damage mechanics. We're not going to touch on damage mechanics. If there's time at the end of the course, we can talk about it. Damage mechanics gets to be a little. It's not really plasticity, so it's a little more conceptual, a little more difficult to explain. And so I want to not touch on. I don't want to talk about damage right now. How? These are all phenomenological models, so you can incorporate features of damage in the context of a plasticity formulation. However, classically speaking, what damage means is that you have what's called void nucleation, growth, and coalescence. You have these voids formed like in a metal. You take a piece of metal. For those of you who've done the dog bone tension test, you pull like a piece of steel. Eventually, it'll start to neck. And in the necking region, if you have what do you call it, like an optical microscope or some sort of, these days, a digital camera can give you enough resolution. You look at that necking region, you'll start to see these holes forming. Those are what we call voids. What that will do is it will make, I'll show you in a moment, it will make the stress strain curve start to bow over and eventually come down as you fracture it. In constitutive modeling, oftentimes that's what's called a ductile damage theory, where you have plasticity, but you also have damage, meaning these voids are growing. And what happens is if you were to unload, your elastic modulus will now have changed. And there are thermodynamic implications of that, which are a little difficult to explain, this is the reason I'm avoiding it for now. Okay? If you're interested, we can talk more about that later. I just said this. ISVs are phenomenological, trying to capture lower length scale behavior, so motion and piling up of dislocations and obstacles in metals, or compaction of pore space in a sand related to shear strength, etc. Okay. Right. Okay. Now, okay. So the nice thing about elasticity theory is, without damage, of course, is that all you need is the deformation. All you need in this case for finite elements, all you need are the nodal displacements from which you can calculate the interpolated displacement field from which you can calculate strain. And then at any period in your loading history, you can calculate stress. However, that's for just standard elasticity, or even this sort of fictitious elasticity model I gave you for the problem set due Thursday. However, for plasticity, there's this sort of memory in the material. So now we have to track these variables over time. And so what we do is we take our equations and we take our Hooke's law, okay? So for so what did I do? Number 1, and then just to be consistent, so we did number 2, balance equations. And then thermodynamics. I'm not going to write everything up here because we're going to get into this in more detail. Dynamics. And then number 3 was the constitutive modeling, which we're also going to spend time on. Okay, good. And then 4, so these constitutive models will be in rate form. Let's say that there's material with memory. Okay, and this memory is going to be something like a yield stress or something like that. So why is that important? Is from the perspective of nonlinear FEA, we have to numerically integrate these in time. So numerically integrate constitutive equations in time. Okay, so these are going to be ODEs, or system of ordinary differential equations. All right, so classically speaking, so if we have Hooke's law, this is probably the simplest place to start. So we're going to have something like this. Okay. Then we're going to have the rate form of this. So the rate form. So the rate form of Hooke's law, assuming the elastic modulus is constant for right now, but this would be sigma dot equals E times epsilon dot E, where this dot is the time derivative. So we say that sigma dot is equal to D sigma dt, that. So we assume, so you can see here already we're making an assumption, assume E, the Young's modulus, is constant. So if we wanted to do thermoelasticity or thermoelastoplasticity, we could have E be a function of theta, the temperature, but then we just have to account for that. And that's possible to do that. But we're going to ignore that as well because it just complicates the equations to this point. But what we're going to do is that we're going to, but we know from our kinematics that epsilon dot E equals epsilon dot minus epsilon dot P. So we're going to have a flow rule for this equation. So a flow rule, we'll talk about that in a moment. And then this is going to come from our FEA. So this is going to be approximately equal to delta epsilon over delta T. Okay, and this is like our over time. So for example, this is our epsilon n plus 1 minus epsilon n over delta T, some pseudo delta T. So some of you were asking, and I left some of that in the code for what you're working on for Thursday. Some of you asked, well, why do we have this delta D in the MATLAB code, this capital delta D? And it's associated with calculating this delta epsilon, which we're going to need to drive our constitutive model. Okay, so for elasticity, we don't worry about it. For plasticity, we do. Okay. Okay, so that's what that says. So what we're going to need to do is we're going to have to integrate our constitutive equations. They're going to be ordinary differential equations, and you'll see how it works out as well.
Last one.
Oh, these are, so n plus 1, epsilon n plus 1 minus epsilon n. Okay.
Sorry. Thank you.
Yeah. So in our finite element method, like within the, let's say this is all happening within the element, we'll still have, you know, epsilon n plus 1. Let's say this is now within the element, h of e. This is going to be equal to our strain displacement matrix. E is where it gets confusing. This is element, not elasticity. So this is element times our, again, our element displacement n plus 1. So this is being updated by our finite element method. Let's say we, again, do the global degree freedom map down to the local degree freedom map using our location matrix. We can pull this from the global D that's being iterated with the Newton-Raphson algorithm. Eventually, there'll be a k plus 1 here. This will be a k plus 1. Okay. Yeah, so what I'm trying to say here is that eventually, stress, we're going to have to integrate this equation in time. And it's going to end up pulling this integrated form from the element analysis with a total strain that comes from the finite element analysis. And then we're going to have a constitutive equation or a flow rule for epsilon dot p. Now, for our purposes, for the 1D case, this is going to be very simple. But for those of you who work in constitutive modeling already, this equation can get complicated really quickly, okay? Depending on whether you're looking at, depending on what material you're looking at. Now, what's interesting about this is even though there are time derivatives here, what's interesting about this is we're going to start with, this is still going to be a form of what we call rate-independent plasticity. So the time derivative is going to give us the ability to track variables or to track the memory, i.e. the yield stress, but depending on how quickly you apply your load, won't make a difference. Okay? Whereas with viscoelasticity, viscoplasticity, poromechanics, the time will be physical, and then how quickly you apply the load will make a difference. Okay.
So let's see.
So there are whole courses that spend their time on basically, three. So they're basically whole courses that spend their time on 3 and 4, or 3 and then 4 as a way to implement it in a code. We're again trying to cover the whole big picture of the problem, so we're not spending as much time as some other courses might do. So what I mean to say by that is we're really interested in how do we get this into a finite element code or some numerical code. And the next step, aside from integrating the equations and having the stress and the strain and everything else changing over time, we need our constant tangent. So you're going to see how that works. And again, the equation, having the nonlinear elasticity example due this Thursday, you're going to see that the form of the code that you're working on now is exactly the same, except that how this d sigma d epsilon is calculated for an elastoplasticity model will be different. Okay, but otherwise, the structure of the nonlinear finite element code is exactly the same. Although we will need to, as I said, some of the lines of code that I probably should have deleted in the MATLAB code that you're working on for Thursday have some of this memory information in there, but we'll get back to that later. All right, so that is mainly what we're going to be focusing on in this topic coverage of the course, steps 1 through 5. 5. Let me just put it up on the board to be complete. So 5 will be FE implementation. Okay. And then we also need the consistent tangent, so need consistent tangent. Okay, so it's going to be this d sigma d epsilon. All right, we'll get to that later. All right, so that's going to be the focus of this next module topic coverage. Now, but one thing I want to point out is some of you even asked me about your projects already for the class, the final project. So there are additional steps in constitutive modeling that we should be aware of. And this is something we will be doing to some extent in this class. And you will see this starting with the next problem set, which I hope to give next week, which is you're going to work with these equations in a kind of, right now it seems very foreign how to do that, but pretty soon you're going to see how to do this. Is you're going to be working with these equations by hand, I call it. Okay? So you're not going to worry about a finite element code, stuff like this. You're not going to, but you're going to worry, like you're going to take these equations and like given a strain, you're going to calculate strain or stress, and you're going to drive your constitutive model. You're going to draw curves like this, and you're going to find points like this, given actual numbers for, let's say, sigma y, and however far we're deforming it, and you're going to find numbers like this. And you're going to do that by hand. And what that's going to allow you to do is that eventually, when you get to a numerical implementation of the model with regard to actually doing this in a finite difference way with respect to time, you're going to be able to check both an Abacus user material subroutine implementation, a MATLAB implementation, and and you're going to, quote unquote, try to verify your model. Now, classically speaking, the best form of verification is if you have a closed form solution. Now, with nonlinear problems, that's very difficult to have. In this case, because the problem, the way we set it up, is somewhat simple, this by-hand calculation will allow you to do sort of a pseudo-verification of your code, okay, to check that things are implemented properly. I'm just referring to some other, and verification has different meanings for different communities. In solid mechanics, there's a classical reference here. Fluid mechanics, it might be something different. Okay, so this will be something we'll also emphasize to some extent in this course, not as much as in the linear finite element course, because in the linear finite element course, we did actually have exact solutions that we could compare to, and you guys did your convergence analysis with respect to refining your mesh. Let's say for the heat conduction problem, you remember the Gibbs phenomenon at the corners where you have a singularity of temperature. So you checked all that. Okay, so we'll make sure we do some of this. And then for your projects, for those of you who have experimental data, we'll be doing likely what we call a calibration exercise. So what this is you have experimental data, you have now a model, and it could be already implemented in Abacus, or you could implement it yourself, depending on, or another code. And some of you are already doing this. You basically take your model and you try to fit the data, or calibrate your parameters such that your model fits the data. That is called calibration. Okay. Now there's the last step. Well, there are two other additional steps, and the eighth step is beyond the scope of this class, and is quite challenging. Some of you have already heard me talk about this. It's called validation. So even in the computational mechanics community, some people interchange 6 and 8. Some people call checking of your code validation. That's from a literature perspective, at least these days, we try to distinguish between the two words. Verification means checking your code against some either separate solutions or manufactured analytical solutions. Validation, classically speaking, at least nowadays, means can you blindly predict another experiment with your now calibrated finite element model, with a constitutive model that you calibrated to data? Can you now go to another experiment and try to predict the response? And this is typically something that's more structural, not elemental. So for those of us who work in soil mechanics, we have what's called the centrifuge test. That's a great way of validating your model. Or some people use this as a way to calibrate the model. If you do that, then that's not validation, that's calibration. Structural lab test. Or this could be some realistic component loading. So for example, a classic example is the automotive industry, the car crash simulations, right? That, I should say, in the automotive industry, they've spent so much money on these numerical codes, as well as calibrating these codes against the data, that really they've invested so much money in this 6 through 8 that it kind of gets fuzzy, or 7 through 8, it gets kind of fuzzy what's the difference between 7 and 8, okay? What I mean to say by that is there are, some of you have heard of this, there are what are called grand challenges out there, where someone will conduct a test, whether it's a car crash simulation, or a centrifuge test, or some other sort of structural sort of component or multi-component test, and they'll tell you the loading conditions, they'll even give you the material properties, and they'll tell you, okay, go with your computational model, now predict the response, and you have to come back with your prediction. And so oftentimes with these predictions are sort of, needless to say, kind of spread all over the place. Not oftentimes are they actually predictive. What I'm trying to say here is with respect to validation, you're actually trying to blindly predict this response. There's some keywords here that I'm not touching upon, and that is uncertainty quantification. So with respect to this validation, what you would also be attempting to do is to quantify if your model is not actually predictive, why is it not predictive, and where is it lacking? And that falls into another area of computational modeling called quantifying your uncertainty, which is even further beyond the scope of this class. But I'm trying to put into perspective what we're doing. We're very much myopic in what we're trying to do with respect to constitutive modeling, because we can only do so much in the context of a course. And assuming you've done 1 through 8, if you're even successful getting past 8, then you should have some confidence in actually using your finite element analysis. Right?
That's the idea.
Okay. Let's see. Any questions at this point? Yes?
Doesn't matter the difficulty of the problem. As long as you did something before to calibrate the parameters with another test, then you call validation when you are using centrifuges. But if you didn't do that, you call calibration even when you are using geotechnical centrifuges.
Yes. So the question is, yeah, kind of the difference between 7 and 8, or if you're doing 7 or doing 8. Yeah, so it is possible sometimes, yeah, right, as you know, with centrifuge testing, sometimes because the boundary value problem is so complicated, like a liquefaction analysis or something like that, you may not have enough experimental data with respect to a simplified geometry like a track or cylinder of soil, for example, or some other geometry of the soil that you're trying to test. You may not even have enough information here to really calibrate your model properly. So it's possible that you may use this test as a second form of calibration. And that's fine. It's okay to do that. But what I'm trying to say is that then is not validation, because you know the result. I mean, you know the answer, right? And you're fitting your model to the answer. Okay. So that's different than doing an actual blind, where someone at another site does a test on the same, let's say, soil, gives you certain properties, and you try to predict that experiment. That would be a form of attempting to validate your model, and that's much harder to do, as we all know. So, yes?
Interesting. In step 9, like, is that essentially a second validation if you get, or you're doing something that you don't have experimental data, or what are?
Yeah, so here would be like saying, okay, I've calibrated my parameters. Let's say I have some within some reasonable amount of uncertain, you've quantified your uncertainty. Let's say you're comfortable with that. Your model is somewhat within the error bars of the data here with number 8. And now you're saying, okay, now I'm ready to use this model in a more design or sort of, I wouldn't say, I don't think any models are really purely predictive these days, but you would basically have a lot of confidence in your model to potentially apply it to some other similar sort of boundary value problem. Now, granted, what I mean to say by that is, let's say these are sort of dynamic tests from the perspective of, let's say, an earthquake, but I would not recommend you to use a calibrated and then validated model with respect to an earthquake loading on a soil and rock and a structure, and then go and say, okay, now I'm going to model another dynamic event like a truck running into the building, because that would be a different rate of loading. So you're likely to encounter different material response. But what I would say is that if you go to potentially different location, different structure, let's say the soil is also reasonably well characterized, you could then start to say, you could apply your model. Let's say someone wants a quick prediction potentially of what the response would be, or you want to try to design a new foundation system or something like that. You could then say with some confidence that you can go to 9 and you can do that. And that would be the idea. Now, we all know, and that's a rather idealistic view on things. We don't do things that way because we still realize that our models are deficient and that we need experimental data. So I think it's safe to say we're going to always require some experimental data. Yeah. Anyway, so, but that, I mean, I'm just, from an idealistic perspective, if we can get to 9, that would, and that's, I guess, a goal we all, for those of us who do more modeling, we would try to get to that point, but we haven't yet. So I'll just say it that way. So. All right, so kind of going back to this curve, which we started with in the class, and touching on number 7. This is a motivation from a figure taken from the Lubliner book, and I'll refer down to here on some of the labels on the figures A through F. So A is a ductile metal in tension. So this is kind of where a lot of plasticity theory started. So the idea is with different metals, nickel, chrome, steel being particularly high strength, and then eventually it's in tension. So what I was talking about with regard to the dog bone test and the necking is what happens is like when you start to get the curve coming over like this, then the necking occurs and eventually there's failure. The two pieces separate, okay? Now what's complicated about this, again, these tension tests in particular, is that what's happening here is there is some form of damage occurring, which we are not talking about in this course. But anyway, this is to show that with different forms of metals, whether it's steel or, needless to say, copper and brass are quite soft. So you see a lot of the elastic region is actually quite small, but there's a lot of potential plasticity. For those of you who've worked, you know brass and copper are very soft materials from the perspective of loading. Now, granted, this is megapascals, but still. And you can see here the strain. So this should be some sort of axial component of stress and axial component of strain. You can see here some of these tests get to 50% strain. So that's a very large deformation. Okay, so what's B? So B is a combination of tension and compression on steels or some metal. So again, these behaviors like this, we get these curves that look almost perfectly plastic, though really what's happening is damage and failure. So this is tension and fracture. However, for metals, when you're doing plasticity, oftentimes experimentally, what you'll do is you'll do a series of compression tests. So you'll take a cylinder of material, and this is like an unconfined compression test for those of you who work with like soils and rock, and or concrete also. But it's the same type of test. You put the sample in between two platen. You bring the platen down. Usually it's displacement driven, unless you have some load driven, like some servo control. You try to minimize friction here. So minimize friction. But also, we know friction always eventually plays a role at the boundaries. So what will happen is you'll compress this sample. It will stay more or less. It will stay more or less in a plastic state. You won't get necking and damage and things like that. So that's this curve right here. Goes up like that. So that's something we use to calibrate models with respect to plasticity and compression for metals. Let's see, some other behavior, getting to more brittle behavior. So this is 50% strain. Now this is 4%. So you're talking down like in this region of the curve. So glass, of course, we know is a brittle material. You can compress glass. If you compress it to a very small strain, like just a hunk of glass, you'll get more or less a linear response. Cast iron can also be quite brittle if you pull it in tension. It just shows here how actually if you pull glass in tension, you'll have it, obviously glass is quite brittle as we know, so it will break quite early. Cast iron has some, in compression, it will be more ductile. This, I think, is a rock in either compression or tension. You can see what's D.
Typical concrete or rocks.
Simple compression or tension. We'll get to the soils in the last curve. But what this shows you is that if you are managing to do an unconfined tension test on a rock, so what this is you have, like say, a cylinder of rock, you somehow manage to either grab the rock or you somehow have some really high-strength glue, and you glue the rock and you pull it, you'll get some form of tension. You'll get some failure right here. However, if you compress it, you might see some response like that, although there are other issues here. And you can see these strains are even smaller. That's percent strain, so that's less than 1%. How they can trace this particular post-peak softening curve, that usually is difficult to do with rocks. Usually they break right here, and then that's the end of the test. Okay, so now when you start to get into confining stresses, so what you see here is if you have now the axial stress is not just sigma 1,1, it's what we call a deviator stress. So it's the difference between the axial component of stress, which is being measured this way, and then something called a radial component. So let's say this is sigma 1, and sigma 3, and this is sigma 1 in terms of principal stresses. So in this case, this is our confining stress. So this is rock, just showing that at low confining pressures, almost nearly unconfined, you get a very brittle response. But if you do a lot of confinement up to 1,000 megapascals, for instance, that's quite a large amount of confinement. But then a rock will almost start to look like a ductile material because you're holding it together at such high stresses. So this is, it's needless to say, this is like a rock at some deep depth underneath the earth, underneath the surface, the ground surface. So rocks will deform in almost like a ductile sort of plastic manner. And then lastly, our soils. And the reason that there are no units on here is for those of you who work with soils, you know that these curves be all over the place depending on the soil type. But the idea is that with a dense sand or some, they talk about sensitivity of clays. We're not going to get into that. But the idea is you could have peak, post-peak response in a normally consolidated clay or a loose sand. You get something that looks like more of this gradual loading curve. What makes soils, I do want to make one additional comment before we start getting into some of the equations, which is that what makes soils and rock to some extent, but soils in particular, challenging. For those of you who work with constitutive modeling of soils, you already know this. The plasticity is a challenge, but oftentimes what makes soils complicated is the elasticity. Okay? Because in soils, what does elasticity mean? You know, you start to load a soil. Let's go back to our definition. This is an idealistic perspective on the material behavior. We're saying elastic is recoverable strain, plastic is permanent or irrecoverable strain. The problem with soils is, as soon as you start to load a soil, the elastic strain is almost non-existent because you immediately start to modify the soil in a permanent way. Particles start to move around. You know, it's very difficult to quantify the elasticity of soils. And so even this curve right here, I would say this curve right here, all the way down here, it's plastic right there. The plasticity starts right there in a loose sand. Okay, so, and I'll make this comment, and fortunately, unfortunately, depending on your perspective, in this course, it's all small strain theory. But when you start to work with finite strain constitutive models for elastoplasticity, what makes these models complicated is not the plasticity, it's the elasticity. I know that seems strange, but elastoplasticity at finite strain, it's the elasticity that causes all the headaches. It's not the plasticity. I don't know, it's a little strange to understand what that means, but for those of you who work with these models and you're actually implementing, you understand what I'm talking about. But we'll get to that later. Here, we don't have to worry about these things. Things at small strain, and everything ends up working out a lot easier.
As usual, talk too much. Okay. So we do have a few minutes.
Any questions to this point? All right. So topic 1 was kinematics. Honestly, for the one-dimensional case, there's nothing more to talk about than that. So that's topic 1. So topic 2 are the balance equations. So we're going to start working with the balance equations, and we'll see how far we can get in about 7 minutes. And then on Thursday, we're going to pick up here. Wherever we end up today. There are many more details in the notes, so I'll just kind of touch on some of the highlights. But I do like to write things up so there's some sequence to the discussion. But any questions before I get into this? Okay, so let's just say topic 1 was over there, kinematics. Let's say topic 2, but now topic 2 in more detail. Let's go to right here. And while we're starting to discuss topic 2, I'm going to erase
this guy.
So just essentially. Okay, so, yeah. So I'll talk while I'm erasing this guy, but the balance equation, the linear momentum is what we're going to solve using our finite element method. That's the quote-unquote balance equation. And then the other balance equations, like balance of energy, the first law, we're going to use in the context of the second law to constrain our constitutive equations. So we're not going to solve the heat equation, I mean the balance of energy from the perspective of thermal elastoplasticity. We're not going to do that. But you can extend what we're talking about to do that if you want to. Because there are a lot of materials that are temperature dependent. And if they're temperature dependent, you have to account for the change of temperature. So, okay, good. Let that guy dry. All right, so 2 is balance equations and thermodynamics. So this is kind of the second major discussion point of the talking about constitutive modeling. So the first balance equation we're going to look at is the balance of linear momentum. So I'll call this I. So balance linear momentum. I'll just say solve for displacement U using FEA. That's what you're doing for the problem set 2 Thursday. But it's also going to come into the thermodynamics, as you'll see later. So in the linear FEA course, we spent a little more time discussing this equation, but I'll just write it up here. I'll say in 3D, we have if we have inertia terms, we have the acceleration, and then we have the divergence of stress, sigma ij with respect to xj. We've already taken account of symmetry of the stress tensor here, plus a body force tensor like this. So rho is the mass density. This is a body force per unit mass. You can think about this. This could be the acceleration due to gravity, for instance. This is the divergence of stress. This is the inertia term. So we're going to be ignoring inertia terms just to make things a little simpler. But this is the full balance of linear momentum equation. Okay. Now, you recall, we can put this into the weak form, method of weighted residuals. We come up with our finite element equations. Okay, so we're assuming we know how to do that. All right? So in 1D, which is what we're more concerned about here, is we're going to have rho times A times just U double dot. I meant to say here, solve for axial displacement, because that's what we're worried about here. So this is the axial displacement, U double dot. And remember, it equals this sigma times A, partial derivative or total derivative, plus the body force term, which we just called this little f. Right. So basically, you can imagine taking this equation, can reduce down to this equation, given the loading conditions and everything like that. Okay. All right. So this is the equation we're going to work with right here. But the reason that I'm showing you the 3D equation is that when we get to a discussion of thermodynamics, it's a little easier because a lot of the concepts are introduced in a general three-dimensional way. So it's a lot easier to just work with directly the 3D form and then reduce it to the 1D form. That may, well, anyway, that's what we're going to do. So we have a couple of minutes. If you're interested, there's more definitions in the notes. As I said, mass density, UIs are the acceleration vector. This is the divergence of stress. Here's symmetric stress tensor. Body force per unit mass, so this could be, so remember your units, newtons per kilogram, that's meters per second squared, so that's acceleration, so that could be our gravitational acceleration. Here's the 1D form, etc. And then the balance of angular momentum, which we've already taken account for, tells us that the stress tensor is symmetric, and we've actually written that right here. Because if you do the, we did this in the linear FEA course, and this could be in any sort of mechanics of materials course, but really the way this equation is written for general non-symmetric stress tensors is this I and j would actually be flipped. It would be d sigma ji with respect to xj. But we took advantage of the fact that sigma ij equals sigma ji, and we substitute. All right? So that's something we've already done. Okay, so that we don't have time. But what we're going to do on Thursday, because
I don't want to start it and then end in the middle. The second balance equation is
the first law of thermodynamics. I want to spend a little time on that, and then we're going to get through the second law of thermodynamics, and then we'll start talking about the constitutive equations. So 1, kinematics, 2, balance and thermodynamics, and 3. So we're going to go through this on Thursday, and we'll probably start with 3 on Thursday. Okay? And then I know your problem sets due Thursday, and then on Monday, by the following Tuesday, we should get far enough with this discussion on 3 such that you can work through the equations by hand, and I'll give out the next problem set, which is basically like a thought exercise problem set to have you think about plasticity on paper. Okay? And then the
problem set after that will be a numerical problem set.
Numerical plasticity. Okay. So, good. That's it. Thanks, everyone.
Minimizing friction. Well, there are different ways you can put like. Okay. Oh, okay. Yeah.
We can go to the vector lab. Okay. Let me just finish.
Let's try and hold it in my office.
Okay.
Is that okay?
Yeah, I just have a question because in the very last program, I tried to do the math with the abacus and apply the I think I need to apply, well, I'm expecting to apply force, and I did that, but I didn't work when I applied the laser because the previous file gives force and the displacement. It was like my last point, and then I used the displacement using the static risk. It worked.
Yeah.
It worked. But when I changed my condition to use the thing, but with force, it didn't work. So I don't know what you are expecting.
It should work. It may not converge all the way. So you do. Did you follow the tutorial, like how to set the? Because now you don't, in Abacus for static bricks, you don't set the time increment, you set the delta A. Remember? The increment of the arc length.
Oh, so I need to go back to the previous tutorial to set that?
No. Well, so we ran out of time last Thursday. We basically completed the tutorial. What's the point of doing arc length? But the arc length tutorial, I'm assuming you've done this, just continue with the previous tutorial. Okay, yeah. So, no, it should. Yeah, I guess it's hard to.
Yeah, that's the question that I have now. So
Well, what I can do is, if you can go up to the Bechtel lab now and set up your problem, then on my way up to my office, I'll stop.
Okay, thank you.
Yep.
这个支配来的，这支配是这个内容是什么？那这个是不是？看他画的都是 x y 的。并且它这种。
Oh, auditing.
Yeah.
Yeah, because I mean, we have a balance. I have to erase
But
that
like,
one.
if I will pick the environment, this
The linear course? Yeah, well, depends. Yeah.
I will spend more time.
Yeah, the nodes, at least for this problem, all the one-dimensional nodes are all in there. And I think, yeah, I mean, it is true. There are a lot of details that we cover in linear courses. We just expect you to know.
And like I would like last semester, just in the linear. I had class in School of Mines.
Yep. Oh, okay. So
Yeah, so I could. It was the same time.
Yeah, it's hard once you.
Thank you.
Yeah, that's okay.